Okay. I think we're good to go.
Sweet.
Oh, we should do it so the whiteboard is better seen.
Maybe I'll awkwardly just shove this into my mouth. Can you see the whiteboard?
Did you notice that, huh?
You can also just take a picture of the whiteboard.
Oh, I thought it was just like a box.
Well, what about for all of our viewers, Tom?
For our viewers, oh my god. It's got so many eyes.
Just paying attention to whoever's making noise. And then the panoramics up there.
What app is that?
Nuts.
It's the owl meeting camera.
Oh my gosh.
Comes with it.
Cool.
So cute also. It's a cute little face. Okay, let's do this. So we're gonna learn about the transformer. You can come in. Man, are you going to transform with us?
Does anybody know why the ML box is not reachable?
I switched the Wi-Fi to a different network.
Damn it, Jason.
Was it training?
We're trying to do machine learning.
Just connect to the source network, and then its IP address should be 192.168.0.100 on source this time.
But we're recording.
You can still port forward and everything. It'll be fine.
Yeah, so don't tell any secrets.
Oh wait, you just announced it on the recording, so whatever, it's fine. We'll cut it in.
For our internal IP address, you have to get on the source Wi-Fi to use it.
And our source Wi-Fi password is very secure.
Mm-hmm.
Okay, so anyways, we're starting with what can a transformer even do? So I don't really know, but these are what I can. So the one task you can use it for is classification, which is basically, I think transforming, you basically just like give it some vectors, you give it like some data, and then it outputs some other data, and it's like much less constrained than like a CompNet is. So one thing people have used it for is just classification, and I think that's the thing that, like that's the only transformer I built from scratch, and it was like pretty easy. So I think that would be a good place to start. And so here it's exactly this thing, except the input is just images, and then you bucket each pixel into like 1 of 8 buckets. And then, so now you have, and then you put it through an embedding. And your task then is...
What do you mean to bucket each pixel into 1 of 8 buckets?
Yeah, why are you doing it also 8?
So it's only, the color scale is 8 big.
Yeah.
8 shades of gray to work with.
Exactly, yeah. So instead of having like 255 different values, you make it.
And this is analogous to like word embeddings where you have like 30,000 different words in your vocabulary.
Yeah.
You can distance out to like vectors of a limited size.
Yeah. Or if you have 26 letters, you could have like a vocabulary of 26.
Did you have like thresholds for like the?
Exactly.
Yeah. And just evenly spaced or?
Yeah. And I think that you could probably train a transformer without the embedding and just instead do the like make them like scalars instead of like indices, instead of like tokens. So instead of like bucketing them, you could just say it's like 0.3, 0.6 for each pixel value.
Okay.
And I think that might actually work better, but it's less similar to the generative modeling because you can't do that for characters because like characters don't like neatly transition into each other.
I have a high level question, like why add all this crazy attentional structure when for a task as simple as MNIST, like a regular feed-forward net would also work?
This will work better than a feed-forward net.
Okay.
That's the thing. I think this works better than a feed-forward net for that classification task.
But
it works worse than a CompNet.
How do we know that it's working as we designed it, like as it is on this whiteboard? Versus we have some like whole subsection that's broken, but because you can solve MNIST with a simple feed-forward neural net, as long as there's like one matrix that's doing some kind of multiply and we're back propagating to it, it's still, even though it's broken, learning how to solve MNIST.
Yeah, I think that's a really good question. The thing I would do is like see if using this architecture you can train MNIST to higher accuracy than you can with just like use the same number of parameters in like an NLP with just like stacking regular fully connected layers.
That's a good test.
Let's see if you can match the performance as other papers that use this on MNIST or get close at least.
So the way I knew that my like MNIST classifier was correct is Alec Radford had like a gist that had like that did this task and my thing did as well as his.
That's cool. some sort of benchmark. Otherwise, I mean, isn't that the hard part about ML? It's really fucking hard to know.
Hard to know when you did it.
Yeah.
Yeah, I think that's true. I think Jason's question is really good too, like, why not just use an MLP? I think the thing there is like, you should benchmark it against an MLP. And so the place where, I think this is like a useful task, cause I think, well, yeah, cause it's just like, there's lots of tasks of classification. The like, one where transformer like has really shined is with generative modeling, which if we think about in terms of our MNIST task still, it's just like, okay, let's give it the first like X pixels of the image, and it has to output the probability of the next pixel falling into our 8 buckets.
Yeah, that's right again. If you
So let's, we just want to figure out what the value of this next pixel is.
Yep.
And so that is like our target pixel.
We're doing language modeling or image modeling?
This is image modeling.
Okay.
I just put language modeling because that's like what people will call it generally. Right. Like language modeling is like a big field, whereas image modeling, like less people care about yet. So.
Oh,
Yeah.
cool. So they can actually even tell you like what it looks like. Oh.
Yeah, so for this, you can use it to generate like new MNIST images, and you could like either do it conditional on some and go through our model here, and then finally our model would output the like the logits.
And these previous steps were important because they needed to know what came first. It wasn't just because we had to run through to search for the last.
Yeah, each one needed to output like the hidden state, which the model takes in again. And so the like big thing that's nice here is that instead of having to like pass through the same thing, like the number of times to get to this like pixel, you just do it once.
is this your Softmax classifier, or is that something different?
This at the end.
Yeah, this is the logics.
This can be anything that you want to output, but yeah, you would put it through a Softmax
Okay.
classifier after, if you were training it.
Okay.
Or, yeah, if you just did Softmax, it would give you the probability of each
Of the 8 different buckets that you assigned it.
Exactly, yeah.
Then how would you return that back into so
You could just take the max of all of it.
max it?
And
Or,
that-
but I mean, like, it's in a bucket, right? So it's like one of the 8 buckets, so you can just
Oh,
like,
yeah,
take
you
the
take
mean
the
pixel.
mean, or I don't know, yeah, I think the mean is probably what I would do. Does that make sense? And you can actually like, so this whole thing then kind of looks like a transformer kind of like just turned on its side, because the transformer has like 10 steps or whatever, or it'll have like 14 steps, and this thing has like 100 steps. But in the transformer, at the beginning, you let it see all of the pixels, whereas for this thing, it can only
One
each
by one.
layer, yeah, it just sees pixels one by one.
Cool.
And so in particular, like the computation here at the very beginning doesn't know what pixels are going to be later on. Whereas with the transformer, like you have several blocks here. It like looks like this on the inside. And each of these blocks can see all of the pixels. So even the first block can like look at all of the pixels.
Does the attention change? Is it like obviously like if they can see other pixels, there's an order in which they can see the other pixels in there, and attention might change in relation to others because they might think I'm the most important thing in the sentence, and then they see something else. So it's like, oh no, they're the most important thing in the sentence. Why does that happen?
In between each of the layers, they have an attention where they can look at the previous layer, and so they can like
Adjust
each of the different like states in it can look at the previous layers. And in the same way here, each of the states can like look at the previous layers, but they're getting access to like one new input pixel each time, whereas this one has access to all the input pixels at the beginning. That's my like uneducated opinion on how it works. Oh, I'm gonna grab some water.
No, I can grab it for.
Here, I've got a big water bottle. Okay, yeah, if anyone has other questions about the RNN thing, otherwise we could do the KQB.
Yeah.
to the KQB.
Let's do KQB.
Hey, there you are.
What up, Dagger?
Gotcha.
Hey.
What's going on? Can you see, so you can't see any video, right? How delayed is that? Alright, I'm waving my hands around in a circle right now. Tell me when it starts.
Did you figure out what the shapes are of the KQB?
There.
Alright, wow. Time to check the video, huh?
I've got water for other people if they want. This is
Oh,
mine.
thanks. Well, guess she's staying downstairs in bed, right? Yeah, I think that's fine. Right. All right. Well, you can listen along. You can see the whiteboard. The video's not updating that often, Tiger. And then we'll start a PyCharm session, and we can invite you to collaborate in on that. We'll all be like together in real time. And then we'll hear you if you want to say anything in real time.
So I didn't quite understand, Tom, like what the query key and value were like representing from the word.
Yeah.
Let me find my
So
I think I understand the query and key, but not the value.
Okay, I understand the value. So together,
Right.
we understand the whole thing.
So, query key and value, my understanding is like, if you had just a regular, fully connected attention thing, then it would be hard to distinguish what part of each weighting that connects a word in your input sentence to a word in your output sentence was due to the meaning of the input word versus what part of that weighted connection would be due to the part of the output word. And so the query and the key are a way to distinguish those two factors. This is just my guesstimate, by the way, so don't take it with a grain of salt, but the query is the part that's relevant to the input word, and the key is the part that's relevant to the output word. And so when you're doing self-attention, you're computing the query of, let's say we're trying to produce an output vector for word number 1. The way we do that is we multiply the query key for word number 1, because every word gets their own query vector, every word gets their own key vector, every word gets their own value vector. So we multiply query 1 times key 1, query 1 times key 2, query 1 times key 3, etc. And then we get 8 numbers, and then we sum those together, and then we do some other stuff, and then we get the attention vector. And so what the query vector for word 1 is like, what part of this attention weighting is relevant because of the meaning of this word in the input sequence? And all of the key vectors are like, okay, the weighting from this input word to all the other words should be like weighted by this much, or like that's where we learn what those things are.
Yeah, let's draw it on the board. So I like using, do you guys know like Einstein notation? I think
What
it's
is
like,
INSA?
it's like an Einstein summation, and it like is basically just a nicer way to write matmoles, because I always get confused by like what happens with the dimensionality in matmoles. So like the Einstein notation is just, you have like, if you're multiplying like some vector that has like some input size A and some input size B, and then you want it to have shape at the, or like you have some vector AB and some vector that's, or some matrix that's shaped as AB and some matrix that's shaped as BC. You just say AB times BC equals like AC. And that'll do like a matmole. And it's just saying what the shapes are. So like that's the equivalent of doing like this matmole that's shaped like this. It's like A times B times a matmole that's shaped like this.
Yeah.
Which which is like C by.
So it's a more expressive way to write matrix multiplications.
This is B by C. Yeah.
Yeah.
Exactly.
That's
yeah.
much better than. Yeah. I think it's the hardest part of a lot of these things is like keeping track in your head of like the dimensions of like every step along the way.
Totally, yeah. So I basically, if I ever have a matmul, I'll write it as an Einstein summation instead, because then I won't like accidentally transpose it the wrong way.
Yeah.
And, like everything will silently.
That's awesome.
fail.
T and I were trying to do that down here too.
Okay, yeah.
We get confused when you get like more than two-dimensional matrices.
Yeah, I mean.
Yeah.
So.
Is the key there to like do the same thing, but you just reshape them to two-dimensional matrices?
Sometimes it is. Also, you can just do the Einstein summation, and it'll like reduce down anything that's not in the output. So in this case, like B isn't in the output, so Einstein summation will just like remove B and just like sum them all, and that happens to be a matmul. So let me look up what the like computation is here in terms of like non-Einsteins. Okay, yeah. So in our thing, it like for self-attention, it's BKL, BQL. So this is
The key times the query.
batch key length
Okay.
times the batch query length, and it outputs the I think QQ. Let me double check.
Yeah. The score?
Yeah.
Yeah.
And then, yeah, we call that the score. Is that what they call this?
Yeah,
BQK is how I did it. So this thing here is the scores. And so what this has basically done is it did a dot product of each key with each query. And so these things here each represent the dot product of the key and the query summed along the L. So L isn't here in this output.
So dot product is you take two vectors of equal length and you multiply each of the corresponding elements and then you sum those products.
Exactly. So like both, you can, if we just look at like KL and QL here.
Yeah. 64 by 1 and 64 by 1.
Yeah. 64 is our length.
Yeah.
Yeah. So this is like 64. And let's just say, let's just say that our length is going to be like 4, so I don't have to write out a bunch of numbers. So this might be like 0, 1, like 2, -1. And this, let's say, is like one of our K values. And this thing here is going to be one of our like Q values. And let's say it's just going to be like 1, 2, 2, 1.
Okay.
So
that's 5.
yeah, exactly. So yeah, we would just like sum them together.
Multiply them together.
Exactly. So it's
That's
0.
the value.
Yeah. 2. This is the score for -1. And so then summing them is what Jason said equals 5. So this is just like doing a dot product. And so it like doing an einsum like this will do a dot product in anything that's not in the output. So you can see that in the original, like this is just the matmul.
Oh,
We did a dot product across all of the B's. And so each output here is going to be the dot product of like the A with the like corresponding C. So that's why I like really like the Einstein, is it like makes it more clear how to do like big matmals that have like transposes and blah 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 without having to like get all the fiddly bits right.
So, wait, Tom, I'm kind of confused by this diagram here.
Yeah.
So what's the value then?
Cool. So after we get the score,
Yeah.
so there's I guess like 3 steps in this whole thing. This one is just like this score you can think of as just like if we're doing a lookup in our like if we have some keys and some queries
Yeah.
and we do a lookup in them, like how much do they match? And you're saying that the like a high dot product means that you have a high score. So like your
Okay.
your previous layer can like make some query that's like I want to look at all of the things that have shape like 0, 1, 2, -1, or that have like all of the things that match this query, and then
Basically things that are similar to me.
exactly, and then so you take the dot product here, and so that gives you a score, which is like is has a shape now like k by q,
Right.
Okay.
which is like how much each query matched each score.
Okay. So we want to see words that have queries that are highly similar to words that have. Sorry, we want to find words who have very similar queries to other words that have similar keys.
Yeah.
But like, we already have word embeddings for
And
every
let's
word.
call them states at this point. All of the things in the length L vector are states,
Okay.
because they're not necessarily words. They could be like pixels or whatever.
Okay, we want to find states that have similar queries and keys. That's how you want me to phrase it?
Yeah.
Okay.
It's
We-
in like
states that are
queries and keys, or states that queries are.
We want to find the words for which their keys are similar to our particular states as key.
Yeah.
Sorry, query.
Yeah. So you can think of the output of this as being like a. Let's again just think about it as like a 4x4 grid.
Yes. Okay.
So like some things will be, let's say like green is good, white is medium, red is bad.
Yeah.
You end up with something that is like, might look like this, and we have our red. Let's just say green is positive, red is negative. White is about 0.
Yeah.
You end up now with these scores that are like, look something like this, where they're just like each query is matching each key. And its shape is going to be like Q by K.
Okay.
Does that make sense? So each of these scores now is like how much this state matches that.
Okay, so my question is, we already have word vectors for every part of the, let's say that we're doing translation task. The word vectors are the same length as each other. Why not, if we're just trying to find like words that are similar to each other and therefore should pay attention to other similar words, why not just dot product the word vectors directly?
We're not necessarily just trying to find ones that are similar. The like the Q values and the K values have each come out of like different like MLPs. So one thing.
Position, right? So like it's not just like these words are the same, but like doesn't this help you figure out like what should
Well,
come next, right?
Or
The idea was.
I guess the like we have
It's because you wanted to learn the relationship between words. You don't just want to like do dot product between word embeddings, you want to like learn which ones should be paying attention to which.
yeah. Let's drop the batch also. I think that just makes it more complicated than meaning. So let's just think about it in terms of KL times QL equals QK.
Yeah.
So this is just this is just a matmul. So it's exactly the same as this one up here.
Yeah.
Wouldn't the Einstein be like QL times LK equals QK?
It'll flip them for you,
Oh.
which is nice. That's one of my favorite things about them. It's like
Oh, you can find a way to
What
make this.
flip them for you?
the Einstein. So like there's only one way where like
That would
this
fit, right.
thing fits.
Right.
Oh, super cool.
So it
So-
figures it out for you.
So it'll swap the two and then transpose KL and then it'll work.
Yeah, Einstein basically does like
This is a method in PyTorch or something?
like NumPy, PyTorch, TensorFlow, all have Einstein.
Isn't that only true if they're not equal?
Say that again.
So is it only true if they're not equal, right? Like if they were both 2 by 2, we can do either way.
Yeah, but you say, like, you actually give it the strings like KL, QL goes to QK, and the K is the first element, the first matrix. So it's like
That's awesome.
So basically Einstein just does like some sequence of like transpose, mapmol, and reduce. And it'll just do like the correct like sequence of transpose mapmol reduce to get you the shape that you specified in the output.
That's amazing.
So you were asking about the like if you like why not just look up the closeness of each word with the other word. That would be the same thing as if you like you only had one thing. So if you did like KL, KL goes to KK, that would be figuring out how close each word is to itself. And we don't want to do that because we have like a different query. So like the query comes out of a big neural net and the key comes out of a big neural net. So they could be totally different and unrelated. And then the like transformer block is about like letting the model figure out what things to query for and what things are like useful keys to provide.
Oh.
And so each transformer block gets to make a new kind of like little database that's like, this is how our keys are mapped, these are how our queries are mapped, and these are how our values are mapped. And this might make more sense when we get the value part too.
Okay.
Okay, so what are the values at?
So basically what we do now is we have these scores, and the scores then we pass through a softmax to get like the attention values. So attention just equals scores, just equals the softmax of the scores. And I think we do a reduce softmax on this. Let me double check what my code is.
Why would you do a reduce?
No, you're right, we don't.
There was something about dividing by 8 at some
Divided
point.
by 8 is just
Just
the number
stabilize
of heads, I
ranges.
thought, right?
Yeah, there's a
No,
dividing
dividing by
by
8 was like part of the
you
self-attention.
scale it. I don't think that part matters. I think you can not do that and it's okay.
Yeah, that makes sense.
Oh, it's just the square root of the dimensions of K.
Yeah.
Yeah.
So that's just changing the temperature of the softmax.
Okay.
And it just makes it so that you're, like you can change the number of heads and it won't affect the like output of the
Okay.
softmax. Like the softmax won't be peakier or less peaky. But I think it'll work if you don't do that.
Interesting.
So we take the attention equals the softmax of the scores along the dimension equals -1, which is the K dimension. And so taking the softmax basically means that now everything along this K dimension will have to add up to 1.
I see.
Cool. And so then.
So now we have like, do you guys think that this is still useful to have?
I took a picture of it already.
Yeah, I might just erase this.
So is value that whole.
So this is the attention, and then we multiply so maybe it's good just to like look at what this looks like now.
Yeah.
So now this is the same, like each of these values, like the green ones are still going to be higher than the red ones, so it's still going to look like quite similar, but now they're all going to be positive because they went through a softmax, and they'll add up to 1 as you look across the key dimension. I'm trying to figure out which ones. I guess rows are the first one, so along this dimension. Yeah. So like, if you add all of these guys together, they add up to 1. So let's just say that what that means is that only one of these can be green, which is like the highest value,
Yeah.
but there also could be like other ones. So like this. So like this would be an example. So let's just say that like these can generally be scalars, but they can't be. Yeah, these like are scalars, so they're not just like on or off, but like you can't have something like this because now you have 2 in the same key vector. So each of these can only add up to 1. So you know that like it only is going to be like focusing very hard on like 1.
Okay.
Because that's what the softmax does.
I mean, wouldn't it be possible for Softmax to produce like a 0.5 and a 0.5 in 2 separate places?
Totally.
As long as they add up to 1.
Totally. Yeah.
So what are the values?
Yeah, so we'll get to that. So this guy just like adds up to 1. And so what you can think of this now is that like each of these, now we've done this across the k dimension, so now each like of this attention dimension of the second part will sum up to 1. So the now we have something that's shape is still qk, and we have one more like mapmul that we do. Which is
So each state gets their own key vector, value vector, and query vector, right? Or state word, or whatever we're referring to. Okay, so each word has its own.
Each state has its own query, key, and value, yes.
And that's all determined by like training, like a training vector that we came out with earlier. Like how do you calculate key value? Vectors for each?
There's just a bunch of vectors we store for each word, and then they're connected to this big computational graph, and so backpropagation affects them and updates them. Like they're responsible for how well we do with our final task. What's your question?
Like how do you calculate the key vector and value vector and query vector for each?
You randomly initialize them and then you backpropagate. Is that like we pull them out of thin air and then we make them work?
Really?
Yeah.
okay, so this last thing is going to be like
That's the part that was confusing. Was like how do you actually get?
so the values are an input. So our whole thing is like our like attention function. It takes as an input the like key is the KQV, is key query value.
Right.
And each of these KQVs are coming from like the previous layer of the transformer. So like
Wait, could you say that again?
Yeah.
So, go ahead.
Wait. So I was gonna say that doesn't sound right. What you just said. Because I'm asking like, yeah, how do you get the where do you get the KQV for it when you put it?
Well, when you call this attention function?
Yeah.
I think it's basically like you have something that's like this like big MLP.
Yeah.
And then the MLP has like 3 things that it outputs. This is without like multi-head. It like outputs K, outputs a Q, and it outputs a B.
Yeah.
And then you put all of these things into the like KQV function, our attention function.
Got it. Okay.
And then if that outputs like something new to put into an MLP again. And you just keep alternating between MLP and KQV, MLP, KQV. And like this whole thing here is a transformer block.
And there's 6 of those.
Exactly. is just this like KQV attention function.
Got it, okay.
That's the only place where it's not like an MLP.
Right, so to translate that back into this diagram, the KQV combination business is self-attention.
Yep.
And then the feed-forward neural network is the MLP.
Yeah, exactly.
Cool, okay.
So now we have like, at this point we have some attention vector that's shape is gonna be like Q times K. And we can think about Q, let's just call that like D is like the like dimension length.
Sure.
Cause that's like, and all of these, the K, Q, and the V all have length dimension at the beginning.
I think the paper had 64.
Yeah.
Yeah.
So we can call this like, just do a second matmul here, which is gonna be this like DL by AD, and so the DL is gonna be the value,
Okay.
and the AD is our attention.
In the previous example, I think you were using the letter L to describe the dimension.
That's still what we're doing.
So why D for the value?
Sorry. Dimension is the like the depth of your like KQV. Each of the KQVs
Which
have
is 64.
something and then L. So L in this case, L always equals like in our thing it's like 144,
Okay.
and
Oh.
D equals the same as K equals the same as Q equals 64. I just wrote them out here because we end up with Q and K, so I wanted to keep them separate.
Okay.
Just so it's like more clear what the first element of the output matrix is and the second element of the matrix. Does that make sense?
So L is like the number of pixels?
Exactly. It's the length of the context.
And so now down here we're referring to the number of this is like the values vectors matrix. And it's of dimension number of pixels by the length of the values vector, which is D. So why don't we say VL instead of DL? To make it more analogous to the upper.
Yeah, we could do that. It's just a little bit confusing to say that then.
Oh, the output would be the D.
Yeah, we could instead say here that this is VL and this is AV, and now we're saying that the second dimension of the attention we're actually just going to call V, but it equals V equals D equals like previously we called it Q.
Okay.
They're all the same.
Yeah.
Just I guess this is one of the downsides of doing einsums is you have to give them a letter.
Yeah.
So like, and the letters mean different things at different times. Like first, this dimension was like the query dimension up here. Now we're turning it into the attention dimension. Now it's going to be the value dimension. But all of them are just D. So we could have called them all D at the.
I see.
Okay.
The only time where we couldn't call them both D is at this top, where one of them is the key and one is the query.
Yeah.
So maybe let's just call them D after this point.
Okay.
I think that will be a little simpler.
Got it.
So now this D is like the dimensionality. So I'm gonna call these D. But this is still gonna be our values, and this is still gonna be our attention. This is AD. Attention. And now we output something that's shape is attention L, which is basically like how much, we're basically just at this point scaling our attention, or scaling the values by how much the attention matched them. This one I'm like a little bit fuzzy about how, like what the, what's going on in it. Because it's another matmul, and we're reducing over the dimension. here.
Right.
So we're gonna end up with something that's shape. And let's just say like the L is gonna be like longer than D,
Okay.
because it's 64 versus 144. So I'm just gonna like draw it like that too. So that means that it like, let's say it's like too long by like 4 or whatever.
Mm-hmm.
So now, again, it's going to be shaped something like this because it's the output of a matmul, and there might be like some that are high and some that are low, and it's basically now this is the length, and this is the attention. This is a little bit annoying because before we were saying that let's like A equals D, so it really should be 4, but I just didn't want to draw them all out. And so it is going to be a like value. Yeah, this now is like a weighted value for each of the different contexts. And this is going to be what our input is to the MLP that we put in next.
Mm-hmm.
So it's basically like we took the values that we had and we took our attention, which was saying how much we care about each of these, and we used that to scale something that's going to be the same size. It's going to end up with the same shape as the value input that we came in.
This is friend and guy who's interested in community housing, Toby. He lives in Red Bank.
Sure.
Okay, cool.
He's gonna work on like random Python projects.
Okay.
I just wanted to hang out.
Have you spent a lot of time on this?
I spent like a weekend on it, but I like, yeah, I spent kind of long.
It seems like you know pretty well.
I think what was really useful was just like spending a weekend just implementing this function, because this is like the main function. So let's say this whole thing equals the, like, I call this like the attended values.
So they are
Right, so the attention vector multiplied by the
Yeah, and it's basically the values and the attended values are the same. They're both tail.
right. Okay. And that's always the
So we can call
So
this
welcome.
tail.
Yeah, thank you.
Hey guys.
Hey.
Toby.
Hey.
Michael.
Yeah.
Howdy. I think I know you guys.
I think we've met before.
Yeah. Good to see you.
You too.
Hi.
Howdy.
Nice to meet you.
Michael.
I'm Tina.
James.
I don't know if Jason told you, but yeah, we're also recording.
Yeah, we are streaming on Twitch and recording.
Oh, cool.
Yeah.
I have a lot of watchers right now.
Michelle,
Yeah.
nice to meet
Hi.
you.
Pretty sure it's just my girlfriend for 5 minutes.
Do you have an iPhone charger?
Still my
It's
secrets
working.
then.
Do you have USB-C? Is it new iPhone?
No,
I've got one down in my room.
no, I've got, yeah, I can.
Yeah,
Okay.
There might be one floating around
Your corner?
my
Yeah,
corner.
there's gotta be an iPhone charger in one of these things somewhere.
This one is Tina, this one's taken.
So I guess one thing here is that
I'm guessing Tom will sit here, Tom will sit here. Yeah, one of you guys could take this place.
Oh, that's cool. Maybe I'll.
So at each
And then
step
these
of this
spots are also open.
whole
Actually,
thing,
both these spots next to each other are open.
Yeah.
so-
where we
Cool.
have attention and the MLP, what comes out is another set of weights, or another set of key weights for the key clarity value for each of the words and mechanisms.
you're saying what comes out of this attention function.
No, what comes out of this whole block of like attention and
So I think that out of the attention, the self-attention, comes the attention vector, which is our like attended
attended
values.
values, right? Okay.
Um,
Can I put her arm?
Yeah.
Oh, and the intended
It's
values
just the
has the
opposite
weights
there, but-
for the next key query values what we need if we wanna run attention with again.
sorry, say that again.
I'll go with you.
I guess I'm just trying to figure out like how this all loops. So we have the attention function, is that comes out with each of the values. That's, and that gets passed into the MLP.
Right.
Okay.
Yeah, so I think it's like KQB generates like attention values, like this.
Yeah.
And then they go into the MLP again. And so this whole thing is the transform block. I think people might put the self-attention first normally. So you might say it's like this whole thing is this block. Here's the transformer block. And then this outputs like three things again.
Okay, cool. Okay, cool. That makes more sense.
So yeah, we have like a little KQB, attention values, MLP. And so one thing I'm a little bit confused by still, I think the shape of it, so like let's say this is the attention, or sorry, these are the values and these are the attended values.
Yeah.
I wish I made more space here. So the vowels, these are the attended vowels.
Yeah.
So I think I was confused. I was first thinking that like it just applies like that all of the attended values would be the values, but just like reduced in some amount, because these are all positive. Like the attention matrix only gives you positive things because it went through a softmax. But I think that since it's like its shape is A by D, it actually can just like take these and like shuffle them up however we want. Like each value in here is going to be some like combination of the other things in its row. And so if there's like a positive and a negative thing, like something, this guy that started out green could like become red because it might end up being just like multiplied by this red one.
Because the values is not limited. It can have any value there. Right?
Exactly, yeah. So I think that like you can end up with a big like reshuffling when you go from the values to the attended values. Because so yeah, what I'm claiming is that each value in this attended values matrix, that's our output, can be a linear combination of anything that was previously in the row of this column.
So any linear combination or?
Yeah, so like let's look at a particular one. Let's look at like this guy right here.
Yeah.
I think this thing can take on a value that's any linear combination of the other ones within this row. Right? So if there's like if this one had only like green positive values in the row, like let's say this one, then it could only be green. Because it has to be a positive linear combination of these things, because the attention is positive. I might be wrong about that. Too many things. Sounds like you're suspicious.
Yeah, I'm just trying to think of like how.
I also think this doesn't matter very much necessarily. I think it could be good for each of us to just implement this KQB function. I think it's like the most important part of the whole architecture. We could all just do it in like PyTorch on our own little collab.
Oh yeah, we need collab too.
Collab's great.
I'm gonna take a look. I might just like put in a couple values and see if I was right there.
So all of the weights that we multiply to get like these vectors that we want are from the previous layer.
Yes. All the KQL inputs are from the previous layer.
You mean KQB?
KQB, yeah.
And then additionally, when it does like the multi-head attention, there's like another additional weight that we multiply at the end. And that's also from the previous layer.
Sorry, say that again.
So it looks like for the multi-head attention, we also multiply at the end. We'll have all these different attention. The resulting, we'd have too many like, what's it called? Resulting vectors for the next layer to input, right? So then we then multiply again by a weight that was from our previous training.
You're asking, okay, how does the multi-head attention work?
Yeah.
Yeah, so I think for these things here,
Yeah.
you just, for each of the K and the Q,
Yeah.
like, I think instead we're gonna have something that's like H, like this, where you have like some number of heads, and you just do them all in parallel.
Oh, right, because this, you don't have to do it, okay, this is just the way it's explained, but I guess with math, we can actually just take another
dimension.
Yeah.
Yeah, and then, there, like, with the multi-headed attention, I forget where you actually put it, I implemented it, but basically you just like have to pipe the heads through your
Got it,
like,
okay, that makes sense.
I forget which softmax you go over.
Okay.
But I think it makes it more complicated until we've done the like
Yeah. this is the first one.
non-multi-headed.
They should paralyze it a bit, right?
Yeah, I guess
Yeah,
I was just, I was just curious to know where all these like weights come from.
Yeah, exactly. It's just parallel. It just means you like do attention, but like you have a certain number you do parallel. Okay. I was thinking that it could be good for us just to each in a collab like implement this attention. I can give like some like test cases for it because I think I wrote some test cases so we can make sure that everyone like implemented a good multi-head attention.
That sounds perfect.
I put the solution in the Slack channel too, so people, I think it's fine if people look at that as they're doing it, because I definitely did something.
For a second, yeah. Tell Shy I said that.
I did mine in
so good. Ever seen the kind where
PyTorch, or sorry, in TF Eager, but I think PyTorch is nicer.
TF what?
TF Eager, TensorFlow Eager, it's just like PyTorch and TensorFlow.
TensorFlow with a good API.
Yeah. It's where TensorFlow tried to copy the PyTorch API.
Oh, that's really fun.
It's gonna be the default starting in like a month.
Oh, really?
Yeah.
Really? Are they going to deprecate the other APIs?
No, I don't think so.
That's part of the problem, though, is we have too much. It's like, yeah.
How did you find that? Is that listed somewhere? Because I cannot find any documentation of links through it or anything.
I saw it on someone else's Airbnb page. Maybe it's a recent feature from Airbnb.
Yeah. I think it's just like an undocumented audience.
Yeah, we were
Yeah.
trying
Like I said, we paid like so much money and time
It's
to like,
amazing. Such
Yeah.
a game changer.
yeah. Yeah, that's amazing. Do you want to see some of the tools I have for the project that I made?
Can we do that after this exercise we're doing on transformers?
Yeah. I'll
You're
just
gonna
remember.
hack them for what? How couple hours maybe?
Yeah. I need to put out around like 3:30, but
Let's do it then.
yeah. Cool.
Cool. Yes, it is sorceress, and the password is still alive.
Nice.
See, Jason just gave away her password wrong.
Oh no.
Tom, you put that in the archive spot?
Yeah.
Cool.
Great.
I put it in, I made a transformer channel.
Nice and fancy.
Yeah, sounds good. See you around 4 o'clock.
That's good. Super. Thanks for showing around. Really
Yeah,
appreciate
nice to meet you.
it.
Oh, sorry.
Can I just sit with you?
Is this in the paperclip Slack or different Slack?
Different Slack. Is there a way we could add James?
Can you guys just, could we add me to the rest of the
Okay,
paper
oh,
club?
we can do that.
Would that be easier?
Yeah. I'll add you too, Michelle.
Yeah, sure.
And Michelle, what's your email?
Michelle B for boy, valentine@gmail.com.
That'd be cool. Add both of you.
Can you add Tom feels lucky at Gmail? For some reason, not Tom Brown doesn't work.
Because you did too many hacking.
Yeah, I don't know if that's good.
Tom feels lucky.
Tom feels lucky at Gmail.
Cool. Here, send.
I'm still not seeing it. Can you add Tom at OpenAI?
You sure?
Yeah.
Mine's come through.
Did you change jobs to OpenAI? You're not a brain anymore?
OpenAI.com. What is OpenAI?
Yeah, OpenAI.com. Yeah, I changed a couple.
Congrats. When did you go?
Thanks. Yeah, like 6 weeks ago.
Oh, brand new. Awesome. Liking it so far?
Yeah.
Did they like recruit you pretty hard, or how does that work?
It was, I'd already been like collaborating with some of the OpenAI folks, so it was like, it just made more sense to work directly there as opposed to collaborating between those.
Sweet.
It was pretty easy. Alright, now it worked.
Where are the test cases, Tom?
I need to upload them.
Okay.
We're doing not multi-head attention, but if you can do it with a batched input, I think that would be the way to do it.
Okay. Tina, do you have an environment on the ML box set up?
I would just use
I
Colab
was just
for
using
these.
Colab, but I
Oh.
do have ML box set up for me.
Where's the Colab link?
Oh, I just was doing my own Colab.
You can just do your own, yeah, collab.research.google. And they give you a GPU.
Yeah, it's really cool.
And
you can
it
actually
comes,
get away with doing most of your fast AI stuff just in Colab.
I think it comes with PyTorch installed too, right?
Oh
Yeah.
wow, that sounds nice. New Python 3 notebook.
PyTorch is like a weird name clash with another library that always fucks me up.
Oh.
It's like Torch, I think, too, right?
Is it?
Like, but like when you import PyTorch, you do import Torch. Something weird like that.
Does Colab have any of the nice features that a PyCharm spoiled you with, like autocomplete?
Yeah, that's good autocomplete.
Yes.
Is it there? Alright, I put the link to my transformer, and then I'll put together some questions, or some, should we make a new channel for this, or just general?
Make a new channel actually.
We can call this, transform and roll out. James.
Torch. Let's do this.
Tina. Ish. Jason. There's that one. So I'm going to switch this to whiteboard.
Is this the attachment?
Is that what we're implementing?
I don't know.
Okay, so Tom, we're implementing a function that takes a query, a key, and a value.
Yeah.
Yeah.
Is it,
So let me, I can just put my solution in this Slack lesson.
Wait, can you just give us the signature of the function maybe?
Yeah.
Are those just KQU and the resulting function?
Is this the,
KQU
like,
values?
the corresponding paper? That,
Yeah, but I think that's more complicated
Okay.
than it needs to be.
Okay.
We just want something like this, and then it return the like appended value.
Yeah.
Here, I put it in the slide. Do some stuff. it just makes it into code. So it's like markdown. Yeah, so if you didn't do that, it would format it like.
Oh, so cool.
Yeah.
That's such a, yeah. It's good. Post that.
Can you look at my screen if you want?
Todd, you say this one's more complicated because we're just assuming dimensionality of 1, so we can kind of ignore the D part of it?
We're assuming number of heads is 1, so we still want to do batch KQL.
Okay.
Or batch KQB. You could do it on batch also.
Oh, super cool. So you just write this notation like this, and then it's like, I know what to do.
It figures it out. Yeah.
Whoa.
Are you talking
Wow,
about
what?
the ein?
Yeah.
So yeah, so just to for the implementation that we're doing, it like we'll need it to be batched. So when you're writing your batch, just put a B in front of each of these, and it'll just work.
No fucking way.
So you don't actually ever do like numpy dot dot, like just dot. Like
Exactly. Yeah, I don't use matmul or.
That shit confuses me so much.
Oh, yeah.
It's like where the like how do these things line up?
Wait,
What?
I just did this.
It's amazing.
Einstein Softmax, Einstein QK, comma V.
And it's unhappy.
No, I don't know. I don't have a test
Or is
case.
it working? Okay. Yeah, here I can give you the test
Yeah, can
case.
you give us a test case?
You guys are too fast. I haven't written the test yet. You already got a solution. Here's the test case in TF. You can just convert it to PyTorch. Import torch.
This is freaking weird. Okay. What is it? That's not good. Let's see the good.
Alright, so I'm just converting this from TF. Sure.
Antem's kind of just like a. It's like its
Pseudo-
own little programming language, right? Where you like
Yeah.
input a string as a program, and then like you give
like,
it inputs,
compiles it.
and then yeah, it's a compile it.
It's so weird.
That's what happens when your dynamically typed language doesn't do exactly what you want it to do. You invent a compiler inside of it.
So weird. How often do people use Einstein versus just like transposing and matmuling things themselves?
What's that?
How often do people use Einstein instead of just?
I think if they know about Einstein, they'll do it.
I mean, it seems like strictly
like
better,
strictly
right?
better.
Like,
It's
No,
like
because you can't-
self-documenting and everything. It's like super nice.
Well, but you can't like see. You can't examine intermediate values. You like have maybe. I don't know. Seems magical. Too magical.
you could do
Cool,
intermediate
that's nice,
variables, but you just have to like break it out. Like,
Eat a tree, right?
which page?
The one that was listed?
The attentions or
Oh, who's this one? Yeah, he started an AI company and we were like, I was really excited about it. Then he changed it so it's more like a blockchain AI company with the crypto angle. And I was like,
It got
oh
lame.
yeah.
It got lame.
No, got lame.
Alright, I converted the test case to PyTorch if people want to use it.
Yeah, very good. Same vibe?
Yeah, I updated it in place. Oops.
Would people mind if I opened a window?
No, that'd be great.
Go for it.
Are you warming up?
I can be colder.
Okay, cool.
And if people have questions about the test case, I can try to answer them too.
Type error, A range received an invalid combination of arguments.
When you run it,
Yeah. Did you mean torch.range instead of A range?
What version of Torch are you using?
Seems like the question, doesn't it?
we do torch dot underscore underscore version underscore underscore in Python. I'm using torch 1.0.
O.4.1?
Oh no!
I managed to check mine.
Can you pip install torch?
Which version of Torch should we have? Sorry.
I think torch 1.0.
Pip install torch does not install 1.0 by default. You have to do pip install torch equals 1.0.
I probably don't have it either. That's weird.
Sorry, y'all.
Why would it not install the most stable version
I know.
by default? Oh yeah, I have Torch 0.4.
You have 0.40?
Would you have?
0.41.
I had 0.4. I just copied this like this. Told you.
Yeah, that's what I did too.
Suggested, right?
Just gives you a random collection of torches.
All of the torches that we want.
Must restart the runtime or resimulate install versions.
There was like some bad state somehow. I think because I had TensorFlow at the top and then Torch at the bottom. It was just like complaining at me.
Good.
Generally, if I don't know what's going on, I'll restart it.
Yeah, it's a pretty safe rule of thumb in these collab notebooks.
Cool. So yeah, so my issue was that I had this query thing that was undefined. So that was my
Are you adding a query to the example?
Yeah, I fucked up the examples, I guess.
Yeah, no worries.
Sounds like you ran into my
I literally just got the same error right as you said. So I got this query undefined. I just got that.
Alright, cool. I am replacing it right now. Now we have attention.
Wait, so which version did you have?
1.0. I just did this in the notebook.
Oh, you literally just did
Yeah. If you put a bang in front of it, then it will do a bash command. Alright, I'm gonna try this Einstein hocus pocus.
So this should also work with or without the like softmax scaling.
Oh, without the dimension.
The test will pass either way.
Okay.
Interesting.
And the reason for that is that we, if you look at the test case, the scores and the queries are both like 100, so they're like very large. So when you do the like dot product and then softmax,
Yeah.
they just go to like 1. Like they go to 1 if they match, and they go to 0 if they don't match.
Okay.
Maybe it would be good for me to explain what the test case is doing too. Would that be?
Yeah, that'd be good. That'd be great.
Yeah, let me. Okay, yeah, if you guys actually want to just come around my computer for a second.
Yeah.
So, here's our inputs. So we're doing just batch size of 1, D model is 3, and length is 4. So you can think of that as like, if this was the very first input, that each of these would be like, I guess you could think of it as like an image, that each of these would be like one channel of the input image.
So like a pixel value?
So this would be like RGB. This would be RGB of pixel 2. This would be RGB of pixel 3, RGB of pixel 4.
Can you show me again what the dimension, you called the 3 was D?
Yeah, so D would be like, if you imagine this as like an image classifier, this would be the channels.
Okay.
And so.
So there's 4 pixels in this image.
Exactly.
And
four
would these be
pixels.
bucketed in the 8 buckets that you talked about, or is that?
Yeah,
Okay.
yeah.
So we might condense this into 1/4, where it would have one channel and then the channel was 0 through 8, and there were 4 pixels.
I think, yeah, you could also do that. Yeah, you could imagine these as like bucket values or something too. I think right now, let's just think of them without the bucketing and just think of them as scalars. So each of these could be a float. So we don't necessarily need to do the bucketing stuff.
Okay.
Or you could think of after the embedding. This could be after the embedding. Let's say our embedding just has 3 dimensions that it outputs.
Okay.
So each of these is like one pixel, and it's like after an embedding, the pixel is like 048 is one embedding, 159 is another embedding.
And then, just so I look at another metaphor, so if this was for words, then each one of those would be a word embedding. Okay.
So 159 might be a word embedding for Tina. And you called that D again? What were the other names for the other dimensions? The letters? Did you scroll up?
It was batch size, demodel length.
Okay.
And so length is the like context length.
That's like number of states.
Exactly, yeah.
And then
Context.
It really helps thinking about it in terms of images. Like we say like RGB, like I don't know, I feel like I can like mentally translate that.
Yeah, especially just since
Arbitrary
like
vectors.
everyone has done way more image shit
Yeah.
than language stuff.
and batch size is like, okay, we're just doing one image right now.
That's just parallel. That's just doing it parallel. And the different batches don't interact with each other, so that's why I'm just doing batch size one. Okay, so yeah, so that's our values. You can think of the values either coming in directly from like the embedding, coming in directly from the image, or coming from the previous layer of our model. Let's think about it now in terms of coming from the previous layer of the model. So now we also have a key, and just in this toy key example, I'm just saying that our like previous MLP figured out that it wants to have something in the first channel that looks kind of like this, like 1, 0, 0. And it wants something in the second channel that looks something like this, like 0, or sorry, the key actually searches across this dimension. So at your, it's going to want to find an attention, or it's going to want to make our like attention score for something that matches this like 100, 0, 0, 0 value. So it's going to end up matching this one down here in our query. Sorry, I misspoke. Let's put the query first, actually, because I think that's an easier way to think about it.
Yeah, I agree.
So the like previous layer is outputting both queries and keys and values. So for our query, it wants in the first one for it to find something that matches like 0, 100, 0, 0. In the second one, something that matches or has a high dot product with 100, 0, 0, 0. And the third one wants something that's like 0, 100, or 0, 0, 100. And so I just, for the keys, just made things that like exactly match these. We could also, instead of having them each be 100, they could be like 10, or whatever.
That's why you said it didn't matter if you reduced it or not.
Exactly, yeah. So like if we changed all of these 100s to be like ones, it would also match, but these, and you would get like roughly the same values here, but they would be like more mixed with each other. This one you can really see that like, since they're super high matches with these guys and not matches with others,
Right.
For the first one, it like perfectly matches with this one. So you get the second value out. So that's why this first thing is the second value.
Oh, wait. The value looks equivalent to our embedding.
Exactly. Or sorry, this output attention, the like attended values. And
I thought the values matrix, like the set of values, was like another thing we learned. Similar to queries and keys.
It is, right?
Is it? Oh.
But I think it's just because the numbers we're using in this, that's why it looks exactly.
Sorry, what was your question, Jason, again?
So my question is, are the values equivalent? Are they the same weights as our, like in this case, RGB embeddings of pixels? Or are they a different weight matrix that's learned?
You're saying in this case, like this is just a permutation of this. Like, are they always a permutation? Is that the question?
But the values, you're using that word, but that looks exactly the same as our embeddings matrix.
Yeah, so at the first layer, your values are the embedding matrix, I think.
Okay.
Right.
And thereafter?
Thereafter, they're the output of
whatever
the
that
MLP.
like this layer. That's the next value, right? This one just gives you the next K, Q, and B.
Queries times keys equals values. But I thought that, okay,
No,
so,
well,
So here, it's
When we
basically
use-
like this.
when we use,
The first time, like, you have some input.
so these values are the output of the previous step?
Exactly. So you have an MLP, it like makes a
Okay.
KQB, you pump it through the QKB, you get new attention values, you put it through another MLP, you put it through another QKB, and you just have like 14.
Will you get the QKBs for the next set?
This is like
That,
Q of
that,
t,
that will output the next cake.
it's like Q of t, K of
Oh.
t, V of t minus one.
So do these, so like,
Yeah.
if this was going to the next one, do these
That comes from the last,
KQBs
yeah.
go into the,
So my misunderstanding was that Q, K, and V were all weight matrices, like generated for any given, they were all from the same time step. They were just like arbitrarily multiplied together.
So what do you mean by time step?
And
Eight.
we don't have to go too far into me explaining like how I misunderstood this.
Okay. Yeah, I think it's just like you have basically like your image and it goes through the first MLP and then it becomes like KQB and then it goes through QKB.
Yeah, that's what I was worried about earlier.
I don't know exactly what like this very, very first step is that goes from like image to KQB. I would need to look that up.
Okay.
But for this, it definitely like, we have a KQB and then we do the like special attention thing and we get attention values out.
Cool.
Um,
Okay, so
Would it be useful if I made like a couple other test cases also? Because this one's kind of special where it's like, it has the really high matches, which just make it like easier for me to think about. Where I was just like messing around and being like, okay, well, like, how do you get just a permutation from the KQB?
I think getting more clarity into how the first step produces a V will be
Cool.
helpful.
Yeah, I can just look at that and maybe we can just spend like,
Yeah, how the weights are.
yeah, and we can spend maybe like 5 or 10 more minutes just implementing the KQB.
Yeah.
If you guys want to look at like my solution for it, it actually just follows exactly these like 4 operations. And I'm happy to like, if people are confused about the code, like walk through the code too.
So design
Like,
some.
the code makes sense, but
why
like,
why don't you divide by the square root of d and this step?
Before the softmax,
It should be after Softmax, right?
I think you do the scores before you pass them into the softmax. You divide them by the value.
Divided by square root of d?
I don't. I do that in the code.
Okay.
But you'll get the same result if you don't do it.
How does Einsum know what B and L are?
Let's see. What do you mean?
So in your implementation, this is a very magical function. So K,
I'm gonna put on my glasses.
you have the letters B, K, L, and Q in this string, and you're only passing in 2 arguments afterwards.
Yeah.
So how is it mapping all the letters to things?
It's the dimensions of the first matrix and the second matrix.
Okay.
So,
and it's
BKL, BQL goes to BQK. So key is 3-dimensional, query is 3-dimensional. So the first dimension.
oh,
is
BKL are the dimensions of key.
Exactly.
Oh. Okay.
Which I think is a really good way to do it.
Interesting.
Good job, Albert Einstein, coming up with that notation.
Is there a way to transform BKL and BQL into like QLB? Can you make like any combination of those 3 letters for your output matrix?
Yeah, just try it. Yeah. Yeah. The only restriction is that you can only have the same letter twice in the input, because it will just reduce down things that match up in the input and don't show up in the output.
I see.
But otherwise, yeah, you can just do whatever, and it will like figure out how to do the right sequence of transpose map.
The leap from like AB, BC into AC, I get that. This regular matrix multiplication makes sense to me. But going from a 3-dimensional matrix and a 3-dimensional matrix to any other dimensional matrix, even a 3-dimensional matrix, is black magic.
Yeah, I can explain. So basically, if you could remove the b's here,
Yeah.
and it would be like let's just say b is 2.
Yeah.
So you have 2 dimensions there. If b was 1, it would be exactly the same as the regular thing, right? That makes sense.
Yeah.
Because it just doesn't do anything. It's just like an empty.
Yeah, you can ignore that the one was over there.
If it's 2, you're doing the same matmoles for each of the 2 layers, and they don't interact with each other at all.
Okay, so you just end up with the 2 afterwards as well.
Exactly. So it's just sharding it across 2 different dimensions.
And that's all that the B is doing here?
Yeah, and the B is only doing that because it passed all the way through.
I
It's
see.
like
So
input B, output B.
this equation is just KL times QL equals QK, and the B was passed through the entire time.
Yeah, the B just means that you're doing it B times. You're doing like KL times QL.
And Einstein's trying not to parallelize that? Or?
Yeah, it just won't do anything with those dimensions because it'll only do stuff with dimensions if there's like a difference in the input and the output.
I see.
Is that because it's the first one in the output? Like if that was like the middle term, would that be the same thing?
You're saying like if
Like it's just basically like passing them through and like you're just doing more of these matrix multiplies, right?
yeah.
It's not doing anything different.
Yeah,
So like if you pass through it as the middle term, or if you pass through the middle term, can you do that?
So you could also do like here, you could have it output BQKL, and that would be the equivalent of doing like K times Q goes to L, or sorry, KL QL goes to, sorry, KQ goes to QK.
You need to project that through different dimensions, maybe?
So this would just be doing like an outer product.
Yeah.
Cross product. And so if you had it like this, where you had the L on the output, it would just be doing the cross products and then doing like give you a B by L by QK thing, where it just did the cross product B times L times.
It's still kind of hard to think about, but I do see
Yeah.
what you're saying. It helps when you reduce it by dimension and do that.
Yeah. Yeah, my thinking for it is I'll just like, it's like I generally know what like the input shapes are that I want and the output shapes that I want. And there's always just one way to map from that.
Yeah.
And so I just like give it to Einstein and Einstein figures out how to do it.
Yeah, that's the way to do it.
Alright, I was gonna look at the input.
Where do I get pass values from? Oh, I guess it's B.
Tina, can I look over your shoulder for a little bit?
Yeah,
Actually,
Do you want to sit here?
it's okay. I can sit on the desk. Just because Tom's not actually writing the code, so.
I'm not doing anything fun.
B, L.
So where are you?
So, I wrote a little thing. It seems like, so for the Einstein stuff, so otherwise you would have to just like, within this function, calculate what the batch size is, or like pass that in and then get the length and then the dimensions of it too? And then
You're saying if you weren't doing it, you'd have to like
just,
figure
yeah,
out.
get those values and then like, make sure you keep passing them appropriately.
To make all the shapes match.
Yeah.
Yeah, you'd have to like, I think if I was doing it without the Einstein, I would like try to figure out how to transpose it and how to matmul it to get that like same shapes out. And then after each of those steps, I would like assert that the shapes are the shapes that I had hoped. And that's basically like my like non-IMSUM strategy for doing it. It's like just assert the shapes every time because I'm confused by how the map mole works.
Got it, okay. Do you think it's like beneficial to like keep track of like how to do this, or like is it, because it seems like really nice to use?
The IMSUM?
Yeah.
I just always use the IMSUM.
Okay.
Like I'll either do the IMSUM or do the like assert the shape every time. And the like asserting the shape every time seems like it's just doing the IMSUM but in 2 steps.
Yeah.
Because first I'm like trying to do the calculation and then I'm like checking the shape and the IMSUM just like does the shape for you.
Make sure, okay. Right, because it's always like there's only just like one shape that you would want to have.
Exactly, yeah.
Is there ever a case that's not clear?
Where what?
Where it wouldn't be clear? No, I guess it would only match on like 2 of the dimensions, so it would have to.
Yeah, so like I guess this is an example where you could get the shapes reversed, where like the Q and the K, the like number is the same.
Yeah.
And so if you transposed like K and Q, and you weren't doing the IMSUM notation, you could get confused about which comes first, even if you were doing the assert.
Right.
So I think that's another place where IMSUM is better, where it's like definitely very clear that like Q is the second one.
Right. Otherwise, yeah, you'd have to assert the shape and then assert like that the order of what you did was also what you thought it was.
Yeah, and I don't even know how to assert that.
Okay.
That'd be really hard.
Okay, so yeah, so this is what we're.
Why is attention different to the scores? Oh no, attention is a subset of the scores. Sorry. Attention.
Yeah, so it's.
And what's -1 in this case?
So the second. Right. I'm pretty sure actually I don't even need to put anything there. Yeah.
What library is MPT?
That'd be testing.
Oh, did I put that in the test?
Yeah.
Yeah, sorry, let me.
It should be fine actually if we just do scores. So it's just gonna make all the scores into like the probability, right? Is what I understood from this diagram.
I just updated to have that.
And then to get the next values that we want to play with, it's just using the attention that we have now times what the value that we passed in originally.
And just like to understand the logic, why do you care about defining like dimensions to K? Just because like from that exercise it sounded like K and Q and a few others converge and you'll want to define a similar one later. Like why not just use Q.dim here instead, because you probably will only use it once unless you think that's something you would use later, and I just didn't understand.
Oh, you definitely could have. I think I just like.
Just good practice.
Wait, there's only 3.
Yeah, you can definitely just put it into one. It's because we're not going to use it again later.
Because I remember that, like, for some reason they all converge to this.
Yeah.
Which that bit, I don't totally.
Yeah, so
like,
it seems like the
visualize
dimensions
what
for
you do.
all 3 of these are the same. So like this would equal query.dim also. Make
They
sure
will
that,
equal them all.
yeah. For Tom's I was saying like this doesn't matter as much. And I think there's actually a couple of ways you could have done like getting the score. So like this, we did scores divided by the square root of the dimensions of a K. But it seemed like from the paper here, that you could have gone away with doing it a couple of, like you could do it other ways, but I think this is just actually the most like common way. So yeah, so the third place or divide the scores by 8, which is the square root of dimension of the key vectors. I think we could just do like normalize it, but I guess you could have done something.
What's up?
Cool. But did you see this? I actually think this is like
Is that
quite good. Okay, yeah. Hey.
Again, June.
I can Junius.
Like you just started reading from here.
Well, just for this part, well, if you're curious about just like how this part's done, yeah, I think just reading from, yeah, self attention to detail.
I'm just gonna text my friend, then I'm meeting at 2:30.
Hmm.
I'm just gonna take this.
Oh yeah, go for it.
And lost it.
I think I got it.
Yeah. But
I don't know if that, Tom, in your implementation, what's the other return value from this attention function?
it's the intended values and then also the attention vector.
Oh, is it? Okay, that's probably just because I wanted to print it out
Yeah,
or something.
This is a really good exercise. It's like the perfect amount of difficulty.
Cool. Yeah, I didn't come up with it, but
It's quite good.
I mean, it was like when we were going through the paper this morning, I was just like, oh my god, like
it's like
this
so
is-
much crap.
Yeah, it's just like a lot. So this is like a good like.
Yeah, I think this was the main trick that they had. I figured out what was going on the input too. It just is this. Yeah, it's just the like direct the channels. The image just goes through an embedding, and then the embedding goes past the MLP, and the MLP like splits it up into K, Q, and B.
Okay.
Just by I think it's like you have like 3 little MLPs that each take in the same.
They do the split. They figure out the keys, the queries, and values.
Yeah, one of them makes the keys, one makes the queries, one makes
Oh,
the
so at each step you have to run it through all 3 again.
Yeah.
Okay.
Exactly.
But then what is the weight at the end when you have, okay, I don't remember, not there yet, but with like the multi-head, like, attention stuff, like, what, there's another weight that they multiply it
To make it multi-head versus
Yeah.
not multi-head?
Yeah. Where does that
Uh,
come from?
the multi-head attention, my understanding is just in the same way that we can just make an extra batch thing here,
Yeah.
you can just also add like a head thing in, so.
Oh, really?
So
Okay.
it's like a fourth dimension.
Yeah, and it doesn't interact with the other ones again, in the same way that the batch one doesn't interact with the other ones, so it's just like,
Wow.
so they're just like parallelizing out some different heads now, so it's like you've got, like you can think of that as like, just each batch has like, can do this attention thing like multiple times, or each sample can do it multiple
Right, okay.
times at each layer.
Jeez.
And so, yeah, and like for your change
So that
in
can
your
still just
code-
all be encompassed in like a function that does like attention.
Yeah, I think the way that you would change your attention code to multi-head attention code is literally in your item strings, you just add H at the beginning of each.
What does that allow you to do? What is all
That's amazing.
Yeah, cause like,
It just means
my head
that
is like.
you like, multi-head attention just means that, instead of doing this, like, letting each state attend to, like, do a softmax over one thing, you just let it do it like, if you have 4 heads, you let it look at 4 other things.
Okay.
So, instead of like each state then being like, a weighted output of like 1 softmax over all the other states that you match, it's like a couple. It's like whatever.
So is
number
it
of
soft acting over like a 2-dimensional vector then, or?
Yeah, so you can imagine that like the softmax is like this like attention thing, basically means that you can like look carefully at like one other state, because there's like going to be one thing that's like the biggest element in your softmax.
Okay.
And like if you turned up your temperature really high, it like literally would only be able to look at one previous state. Since the temperature is not that big, you can look at a couple maybe. But let's just say it means you can look at 1. Then increasing this H means you just have like an extra dimension in all of your things. So now instead of looking at 1, you can look at like H things. So they like don't interact with each other.
Is that like, can you do more sophisticated recognition with that? Like if you like have multiple attention, yeah.
I don't really know.
Yeah. I mean, it seems like if you can focus on more than one thing, like you can learn more, right? But
Yeah.
maybe that's just like harder to train, or I don't know.
Yeah, my guess is like that seems like something we can just experiment with too. Is like try it with like 1 head, try it with like 4 heads, see how that works. I guess the trade-off is like if you have more heads, you'll have fewer dimensions if you're using the same number of parameters. So I don't know. There's probably some people who have like really great intuitions about that.
I don't think anybody does. It seems like that's the thing, right? Like,
I guess their intuitions are mostly that like they did a big hyperparameter sweep and figured out which works best.
this paper has a lot of citations in a year. Like a little over a year.
It just works so well.
Yeah.
Is there a potluck next weekend?
I don't know. I think that there's a potluck if someone makes a Facebook event,
So if you want to have a potluck, you can make a Facebook.
but Michelle wasn't
Oh,
on
right,
Facebook.
don't have a Facebook.
Cool. No, I was gonna say I'd invite Ilya to the next potluck, and you guys can note out with him in the paper.
Oh, let's have a special potluck. Yes, potluck.
The other authors have been to our potlucks.
Okay. Cool. No, I don't want to make a potluck just to make a potluck. I will just go to another person's potluck. You know me.
You
I'm
can
not
make, you
an
can make a potluck
organizer
whenever you
like
want.
that. I'd rather organize like a sporting activity.
A sporting activity. Like,
Yeah, like go surfing or teach you guys how to ice skate or like
Oh,
that's
I
the
would
kind
do
of
that.
stuff I love. Like I always go
I do
swimming and I want
Yeah.
something. Yeah, organizing a large social event is intimidating for me, so I prefer not to do that.
It's always like.
But if it's like a sporting activity, the attention's not on me.
I've
It's
been wanting
that,
to learn
like,
how to surf, so I'd be down to go to Pacific.
I surfed it.
It just like the water is so cold that it's
Yeah.
just not fun to learn here. So we'd have to like pick a really warm weekend where the surf's like nice. Or else I'll have many unhappy people with me.
It's really cold.
Well, if you're like just sitting there and not getting up and you're really cold, it's not fun. But if you're sitting there and you're getting up, it's fine if you're tense and you don't notice.
Because you're moving.
And you
Oh my
just
God,
have like
this Einstein
adrenaline.
stuff is actually so bad.
What?
This Einstein thing. I just thought everyone was. It's like it just makes it so much easier to not have like great math intuition.
Yeah.
The answer?
Yeah.
Who has intuition about just like keeping those states in your head about like how large things are and the transformations? Like that's fucking hard.
Yeah, it's like not, computers can remember stuff. for
Yeah,
us.
exactly.
They're great at that.
Like, you ever see those like big nested matrix multiplies and like they're transforming in different places and you're like, what the fuck is the input and output of this?
Yeah, we don't care what they're doing on
Yeah,
the
like it's so hard to think about that. That sounds great.
So for the MNIST task, what
Yeah.
would like do we have like are we gonna write our own like ML like P stuff too so that we get the key query values now?
Yeah.
Okay.
We could like pair code on some of that too, if we're like feeling like we have good attention stuff now. I might want to eat a little bite of something.
Yeah, you gotta take a break for a bit.
Yeah, I'm taking a break for good. What's
What
your
about all of our
guys'
Twitch
schedule?
followers?
Oh yeah.
They can accept it. We'll have a brief word from our sponsor.
I have no plans. I am free forever.
Okay, cool. I'm still having fun, so I'd be into like maybe taking like a 20-minute break or something like that.
Yeah.
Okay, let's do it. See you guys in 20.
Mish, do you want to get lunch?
I'm meeting a friend at 2:45 at Samovar, so I think I might eat when I go. But if you're hungry and you want to go to Samovar, I could go and eat with you there, and I'll just wait for him when he comes at 2:45. Then you get to meet him too. It's up to you. I don't know what you want for lunch. I'm not doing anything, so I will go with you to get
Yeah.
lunch. So whatever you want.
Okay, yeah, so why don't I shower and then we can go stem a bar and I'll just like take something to go.
It sounds great. We can sit for a little bit too.
That sounds great.
Yeah.
Alright, so that means I'll probably be back here at like 3.
Cool.
Okay, I'll meet you downstairs.
Yeah, I'm just gonna shower also.
Sorry, that's what I meant.
Whose bagel is this?
Your girlfriend brought an extra one.
Really?
Yeah.
PLPL?
So
Plain?
I had just eaten like right before I came here.
Plain
So
cream
I
cheese?
said I didn't want one, so she's like, you get hungry. But
Wow. Awesome, that.
I was gonna take a break for like 40 minutes and get some food.
Mm-hmm.
Before I do, I posted just like what my solution was for the like end this thing end to end. I think when I get back, it could be cool to just like spend an hour and try to get that. It could be good also to just maybe like pair code and like trade off on.
Sure. Sounds great.
I'm into the Sunday project sessions.
Yeah.
I feel like with paperclip we've done a lot of like theory and reading and stuff, but like not a lot of implementation.
Mm-hmm.
So this would be good, like, where to get our hands dirty.
Mm-hmm. Maybe we can pair on this machine actually. Yeah.
I read the Book of Why, your recommendation.
Yeah, did you like it?
I thought it was okay.
Yeah.
I thought like he's like a very smart person, and like when he's like giving examples of like how things have previously been done, he's very good at like being very concrete and like kind of leading you from like exactly like how it works and like being very articulate. And then when he goes to like present like his new way of doing things, it kind of becomes like a little bit hand wavy and like the specifics are a little bit vague.
A little preachy.
Yeah. So it's like at first you think like but am I just like not understanding this well? It's like but he did such a good job explaining the other things and like yeah.
It's yeah. At SourceForce we're reading we're doing another book club on something called The Architects of Intelligence, and it's like 23 interviews from like, you know, the pillars of deep learning like Jeff Hinton and Jan LeCun, some skeptics, and then people that are like experts at various interesting questions. Like Demis Hassabis has asked about like AGI, et cetera, et cetera. And a lot of them mention that causality is like an interesting thing to look at more because it's not clear if we have all the pieces of AGI and we just haven't scaled them up or configured them right, or if we're missing like a fundamental piece of the puzzle. a lot of people suspect we're missing a fundamental piece of the puzzle, and that some kind of understanding of causal relationships between things will be that part of that
Yeah.
piece. No one knows if like this specific kind of causality that the Book of Wise, like Judea Pearl is talking about, is that kind of causality that's going to be necessary for AGI. People are actually pretty confident that this specific implementation of causality is useful for something like fairness, which is definitely going to be a near-term issue.
Yeah.
So at least for us, it's relevant to like try and implement some causal stuff, so that we can get in front of like the fairness game.
I mean, it also requires like background knowledge of the domain and like reasoning about it in like an intelligent way, and there's no way to guarantee that like you got everything right. It's like, yeah, like it makes sense when you explain it this way that like A causes B, which causes C, right? But like you can't say that like there was another factor D that also caused C, and
Yeah.
like, it's not like this is the totality of like causation, right? It's
Yeah.
like,
yeah, I would love to see like, you know, in the same way that Tom's like showing us the practitioner's angle on taking on transformers and like separating out the important part from the unimportant parts. Like I'd love to see like a practitioner, like an actual data scientist using causality to show us how it works and like how they deal with like the uncertainty of their model.
yeah, Bayesian estimation.
Jeez. All that stuff plus Bayesian stuff.
And that's the whole Bayesian spiel is confidence, right? It's estimating uncertainty.
So why is this not working? Does this work? Does this work? No. Okay. Swap it.
He's obviously like a very smart person. Like he won the Turing Award.
Yeah.
Alright, I'll be back in 25. See you guys.
You going to get some lunch somewhere close?
Yeah, I'm just gonna grab something at Sam Bar.
Okay. And you guys want to go too?
I'm gonna take a shower first.
Okay.
Did you guys raise money?
It's still ongoing.
Process? How's it going?
Is your keyboard mapped?
No.
Well, the thing is like,
Or can we plug in Tina's keyboard or something?
do you want, right, yeah,
I don't have to
you
drive.
could navigate and I'll drive.
Okay, yeah, sir. Sounds good. Here, do you want my link?
Sure.
You use like Dvorak or something crazy like that?
No, it's just like the modifier keys are all done by your thumbs.
Yeah, and mine I think are actually switched to opposite of what Jason is.
Why don't we just plug in the other keyboard then?
Oh yeah.
Sure. Where's the other keyboard?
Tina, you have your keyboard, right?
Yeah, it's right here.
It is still a little different because command and control are switched for Ubuntu.
What's the output of this screen? Is it a HDMI?
Yes.
Let's just plug in. I have an HDMI to USB-C adapter. Are you USB-C, Tina?
Yes.
Yeah, I have an.
I have a USB-C adapter too.
Yeah, let's just plug that in. Just so that we can cycle through people driving.
On a Mac.
What I was suggesting is this has HDMI out. Just unplug the HDMI and put it in so that we can.
But that
that doesn't work well with the stream.
Because you're streaming the screen and
yeah.
is someone watching?
No, but it's nice to record the thing and then like share it later.
Okay, that's fine. Well, let's just start plugging in my keyboard and see what happens then.
Yeah.
Okay.
Also, let me make this notebook available for everyone.